Hello and welcome again. In the last video we started talking about fast modular exponentiation, and I just started talking about this method of a square and multiply algorithm, which is basically a combination of two operations. One is a square and the other a multiplication by x, and so we want to combine these two operations to do as little operation as possible so we can arrive to the answer. So last time we actually saw this example, how many duplications are required for x to the a modulo n, and so we saw that the best way to do it is to do x squared square square. So I mentioned also in the last video that this will always be the most efficient way if you have the exponent to be a power of 2. But what happens when the exponent is not a power of 2? So before I go into that, I'm going to give you one more example about the square and multiply algorithm. So let's look at this example. Let's look at compute the number of squares and multiplications to obtain x to the 24 modulo n. Now this is all modulo n, but because I don't want to write down modulo n every single time, I'm just going to write down the power. Now the naive method to compute this power will be just multiply by x, and then will require 23 multiplications in this case. Now that will be naive because that will be the straightforward way, which is the definition of power. But there's a better way to do it. So you can see here we have 23 multiplications. If you go out and write down all this sequence here, you will find out that you have to do 23 multiplications. So a better way will be doing something like this. So a better way will be, we start with x, we square first, so we get x squared, and then multiply, we get cube, square, 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 and then you end up with 24. As you can see here, these operations that are here are only 5. So we require only 5 operations instead of the 23 that we require here. So we require 5 operations only, so square, multiply, and then the rest of them are squares up until we arrive to x to the 24. Now remember, with each stage I also have another operation, modulo n, which I didn't write down, but it is there. So it requires 5 operations, 1 multiplication, which is this one right here, and the rest 4 squarings, which is this 4 that you see there. Now the problem is, how do we know what sequence of s's and m's to use? You see here, I just gave you this is the better way, but how do we know which sequence will give me best way to do it instead of doing it all in multiplications? So the good thing is there is an algorithm for that, and the algorithm depends on the binary representation of the exponent. And what I mean by that is this: so if we want to compute x to the n modulo n, when m, I'm going to assume here, is a positive exponent, what we want to do is we want to represent m in binary, and the binary representation of m will give me a method, a very clear method to calculate the number of sequences of s's and m's that I need to do this operation x to the m more efficiently. So before I go into the pseudocode and give you a little examples, I'm just going to give you the algorithm in words. So what is the algorithm? Because we want to compute x to the n modulo n, and as I mentioned, it depends on the binary, the representation of m. Of course, we need to know what the binary representation of m is. So the first step will be compute the binary representation of the exponent m. So I'm going to denote the binary representation of m, which is the exponent, as this is parenthesis 2, and this is h0, h1 to ht. This will be the sequence of zeros and ones that make up the representation or the binary representation of m. So each hi here, each of the h's are zeros and ones, and the first one of course has to be a 1, because if it is not a 1 and it is a 0, then you just ignore it. That's not the first element in the representation. So h0 will always be 1, and the rest of them will be zeros or ones. So how do we do this thing here? So what we're going to do is we're going to read the binary representation of this exponent from left to right, same way you read in English, from left to right. And so if you start with a0, the only thing you're going to do is you're going to write down the base x, which is the base for the exponentiation. Every time you go after it, so for every subsequent hi, we're going to do the following thing. We're going to do always x squared multiplication or a square. Now, if the binary representation of m has an 1, then you apply both a squared multiplication in that order. So you apply s and then m in that order. S first, m after. If the representation of the binary, that digit, is 0, then you apply the square only. So you read this sequence here from left to right as you read in English. H0 will be 1 always, so you start with the x. Then after that you read the next digit and then so on and so forth from left to right. And every time you encounter a 1, you apply s and m, square and multiply. And every time you encounter just a 0, just a square. Just do the square only. So let's see an example and see how that works. So let's compute the number of s's and m's to obtain x to the 24 modulo n. I'm going to ignore again the modulo n in the computation, but it is there. So let's see how many s's and m's we have to do in order to compute this power. So as I said in the algorithm, what is the first thing in the algorithm? Remember, the first thing is you need to compute the binary representation of the exponent. So let's go here to the exponent. The exponent is 24. So we're gonna find the binary representation of the number 24, and you can check easily that the binary representation of 24 is this sequence of zeros and ones, 1 1 0 0 0. So the first one will be my H0. This will be H1, H2, H3, and H4. So as you can see here. So let's start with the first step. So the second step will be just read through this sequence and start applying the s's and m's that we need in order to compute x to the 24 with a few number of operations. So let's see what it is. So we start at H0, which is always be a 1. So I just write down the x. That's the algorithm. Then I read the next one. So the next one will be H1. So you can see here the next step will be H1. Every time you encounter a 1, you apply an s and then an m. So I started with x, and because this is a 1, I apply an s and then an m. So if I apply an s means a square, so I'm going to square the x to get x squared, and then multiply by x, so I get x cubed. So this is the operation here that is H1 is performing on this sequence, applying s and m. Now what is the next h? Is H2. H2 is a 0. And every time you encounter a 0, we apply s. So from the one I already have here, which is x squared, x cubed, I apply s, which is a square. So if I square x cubed, I get x to the 6th power. Okay, the next one will be H3. H3 is 0. Because it's 0, I apply s only. So I already computed at to x to the 6. All of this was computed before, and then I have to square it, so I get x to the 12. And then finally we have H4, which is a 0. So then if H4 is a 0, we apply only a square. So we apply only from here, from 12, we apply a square, and then we get x to the 24. So you can see there, this is the sequence that we get. So we start with x, and the binary representation of the exponent will give me the sequences of squarings and multiplications that I need in order to compute my power. So I start with s, and you can see here I have all the sequence. So the H0 will be this step, H1 will be this two things, which is a square multiply. When it's a 0, you only square, as you can see here in this picture. So it's a very straightforward algorithm. It's not difficult to apply. Now, if you wonder why will the algorithm work? So why is this working the way it's working now? I always write to x to the 24. And if you start with another power and you find the binary representation of that power and you apply this algorithm, then you will end up with the answer. So why does it work? So it works because of a couple of things. Of course, I cannot go into the very neat details of how it works. I'm just going to give you an idea why this algorithm works. So this algorithm works because of the following. Every time you square an element, what it's doing to the exponent is it gets multiplied by 2. You think about it. So when you square something like x to the 4 and you square it, you multiply the power by 2, which is the law of exponents, of course. So when you multiply the power by 2, it adds a 0 at the end of the binary representation. So let me explain that a little bit. So if you have a binary number, let's say you have the binary number 1 1. When you multiply it by 2, this binary number, if you multiply by 2, basically what you're doing is you adding a 0 at the end. That's basically what's happening there. And it will come into play in a second. So you add a 0 at the end. So that happens when you square. Every time you multiply by x, which are the two operations here, squared is what we are doing. So we square. When we square, what happens to the exponent is gets multiplied by 2. That means the binary representation of the exponents get a 0 at the end. And every time you multiply by x, it adds 1 to the exponent in the binary representation. Okay, so let me be more specific about that. So in the example what we had was this. 24 is represented in this way. And we're going to start with x, and we want to end up with x to the 24, which in binary would be this one. Basically what we want to do is we want to build this number, which is the exponent, from just 1, which is this power here. Right? So we want to build this number from the number 1, from left to right. So what do I have to do? So what I have to do is, if I start with 1, what do I want? I want to create the next one here. How do I create that 1? Remember, because we want to create a 1, we want first to create a new digit. So we want to add a 0 at the end, and we're also going to add 1 to that. So if we imagine this operation here, if I start with this, if I add a 0 at the end and I add a 1, I obtain the next digit. So that's why we multiply by 2 and add 1. Multiply by 2, remember, in the exponent means square, and add 1 to the exponent means multiply by x. That's why whenever you see a 1 here, that's what you need to do, square and multiply. Now what do I need after the 1? I need to add a bunch of zeros. I need to add 3 zeros. And the way we add 3 zeros is every time you want to add a 0, remember, here is your square, because squaring means multiply by 2 the exponent, and multiplying by 2 the exponent meaning adding a 0 in the binary representation of the exponent. So 0, I add multiply by 2, which is square, multiply by 2 is square, multiply by 2 is square. So basically that's what's going on here. So what's going on here is we're going to start with this x, and we're going to build up the exponent up to this exponent. And the way you do it is you do it by building this number from 1 from left to right. So you add digits. The way you add a digit is you multiply by 2, which means you add a 0 at that position like we did here, but then you need to add a 1, and if you have a 1 there. So I know this was a very clear explanation of what this is work. This is just an idea to give you why the algorithm works. The algorithm works because of the binary representation of the exponent. So that's basically the algorithm in words. So you can apply this algorithm in words with a number that is, of course, small. When the powers are very large, of course, you're not going to do it by hand. So we have to do it in a computer. So in the next video, I'm going to talk about a little bit more of, I'm going to actually give you another example, and I'm going to talk about the pseudocode representation of this algorithm and how we're going to implement it in Java. So I will see you in the next video.